Today's lesson brings us into the concept of ray optics. This is effectively going to be our introduction into an understanding of mirrors and lenses. But before we get there, we need to understand the concepts of reflection and refraction. So we're going to extrapolate the concepts that we've learned about waves, primarily sound waves, onto light waves. Okay, and everything we're talking about here on light waves pretty much works for sound waves as well, but they're easier to see at this for light as opposed to sound, and the things we learned on sound were easier to see on sound waves than light. Okay. First off, just kind of a review. Okay, all waves obey the wave speed formula, which is the v equals the f lambda, or velocity is equal to frequency times wavelength. For light, the speed is a constant 3 times 10 to the 8th meters per second, as long as I'm in air or in a vacuum. We'll be looking at when that speed changes going through other materials. Okay, all waves can experience reflection and refraction that we're going to be talking about now. In addition, all waves can experience diffraction and dispersion. We won't really talk too much about that stuff until like higher level physics. All waves can interfere with each other, either constructively or destructively. All waves can be Doppler shifted, and all waves can create a standing wave. So everything we've learned about sound waves applies to light, and everything we're going to learn about light waves will also apply to sound and other waves. First off, I mentioned the word refraction. Okay, what is refraction? Okay, refraction occurs whenever a wave hits a change in medium. Okay, we saw changes in mediums before in sound waves or waves on a string. So on a wave on a string, the difference is when I'm on the string and not on the string. Okay, that would be a change in medium. When I am on the string and perhaps I go to a heavier string, that would be a change in medium. Okay, for the air tubes, the change in medium was basically the density of the air inside the tube and then the density of the air outside the tube. And so again, I have this change in medium. Whenever I have that, some of the energy is going to be reflected. And that's how I got a standing wave in the air tubes. Okay, but not all of the energy is necessarily reflected. Some of the energy could be refracted. And refracted is basically transmitted into the new medium, but slightly differently perhaps. Okay, and so this picture shows you the red ray is coming in, the green ray is the reflected ray. Okay, so it's hitting this medium boundary between medium 1 and medium 2, and then the refracted ray continues on. And so we see some of this when we're looking through a window. Okay, sometimes we can see a little bit of our reflection, but we can also see what's on the other side. Okay. So there are a couple of laws that govern reflection and refraction. The law of reflection is this one. Okay, it's a fairly easy law, and it basically says the angle in equals the angle out. This happens with almost all particles. A basketball coming in on the ground will pretty much come back up at an angle equal to the angle it came in on, especially if there's no spin on the ball. Okay, and we measure the angle in reference to what we call the normal. This is the perpendicular line from the plane that it impacts. Okay, so the normal in this case is the red line. Okay, and so the angle on the left side should equal the angle on the right side, and that's the law of reflection. Okay, fairly straightforward. Okay, the law of refraction has a different name. It's the name we apply to it is called Snell's law. Okay, so in this case, I have a ray coming in on the top and transmitting on the bottom. I'm not showing the reflected ray just to not mess up the picture. Okay, but because there is a change in medium from the first one to the second one, I also have a change in angle. Again, I'm going to measure that angle with respect to the normal or the perpendicular line to the interface. Okay, and when I have that change in medium, the speed is primarily what's going to change. Okay, frequency does not, because the frequency of the incoming ray equals the frequency of the outgoing ray. And if my speeds are different, my wavelengths will also be different. Okay, frequency does not change, but the wavelength does. So in this picture, you can see that the wavelength on the incoming ray is fairly large, and the wavelength on the outgoing or the refracted ray is fairly small. And so that brings me to Snell's law. Snell's law basically compares the angles to the two speeds of the medium, okay? And so Snell's law basically says the sine of my incoming angle, okay, theta 1, divided by the sine of my outgoing angle, theta 2, has to equal the ratio of the two speeds, v1 over v2. And remember again, that angle is measured to the normal, not to the interface. Okay, so it's clear the I and the R are the angles that I'm talking about, not the ones to the horizontal line. Okay. When it comes to light, because light has a speed of 3 times 10 to the 8th, a lot of times we don't want to work with that number because it's a large number, it's a lot of zeros. And so we talk about something called an index of refraction. We basically compare the speed of light in that material to the speed of light in a vacuum. Okay, so the vacuum is clearly going to be 1, and the index of the material is going to be the speed of light in a vacuum, c, divided by the speed of light in that material, v. And since nothing can go faster than light in a vacuum, my ratio is always going to be greater than 1. Okay, so here's a couple of examples. Air at 1.0003 is close enough to 1 that we're always going to use 3 times 10 to the 8th there. Water is about 1.3. And diamond is especially useful, and it's what makes diamond as precious as it is 2.42. And we'll talk about diamond in a little bit. Okay, so a couple other examples are given here. But just remember, it should always be greater than 1. Okay, so combining Snell's law with the index of refraction, okay, that says the ratio of the sines is equal to the ratio of the speeds. If I want to use it in terms of the index of refraction, okay, I'm going to do switch it up a little bit, okay, by dividing the top and the bottom of the speeds by c, and that gives me the index of refractions. And this is the format that I'm going to usually use Snell's law in. Okay, this is the format I believe that's on the formula sheet. Okay, and it says that n1, the index of refraction for the first substance times sine of that angle equals the index of refraction of the second substance times the sine of the second substance. It's reversible. Okay, so there's nothing that says this is the first substance, this is the second substance. Okay, in the sense that there's no incoming or refracting in this. It's reversible in that sense. Okay, so refraction concepts 1. Okay, like I said, in the new medium, the wave speed changes, but the frequency does not. Okay, so wavelength must change because v equals f lambda still applies. Okay, and as I mentioned, the index of refraction will always be greater than 1. We have not discovered anything that travels faster than the speed of light. Okay, so there are 2 basic scenarios that we're going to look at. Okay, as long as I have 2 mediums, one of those mediums must be faster. Okay, and whichever medium happens to be faster, okay, that medium will have the greater angle. So air will always have a greater angle than water. Depending, doesn't matter which one's coming in or going out, the faster one will have the greater angle. The challenge here is to not confuse a greater n with a greater velocity. It's actually backwards, okay? Because a greater n implies that that substance is slower than air, okay, by more. Okay, so I would recommend slowing down and saying, okay, greater n means slower. because a lot of times we get confused. I still get confused over this, but a greater n does not mean faster. A greater n actually means slower. And the faster the medium, the greater the angle. Okay, so that brings us to the critical angle. Okay, because if a wave is going from a slower medium to faster, the faster medium will have the greater angle. Okay, so at some point, what is the maximum possible angle in that second medium then? Okay, and that possible 90 degrees is what that greatest angle is, because if it goes past the 90 degrees, it's back into the first medium. Okay, and that's what the critical angle is. Okay, the angle that the incident wave makes in the slower medium, such that the second medium angle is 90 degrees, and we call that the critical angle. Okay, so the math for this is basically using Snell's law, where the second medium has to be faster than the first medium, therefore it's less than the first medium. We basically stick in 90 degrees for that second medium, and sine of 90 is just 1, so n1 sine theta critical equals n2. And so it leaves us with the sine of the critical angle equals the ratio of the two mediums. Okay, and so here's an example. Okay, for light that is traveling from air to water, calculate the critical angle. Okay, and so the incident angle is 1, the refracted angle is 1.33, okay? And so if I plug all that in, I end up with 1 times the sine of the critical angle equals 1.33 times the sine of 90, and I end up with this, okay? And if I punch that into my calculator and calculate the inverse sine of 1.33, I get an error. Okay, why do I get an error? I get an error because I didn't look at the situation to begin with. Okay, remember, a critical angle only occurs when I'm going from a slow medium to a fast medium. And in this case, I went from the fast medium, air, to the slower medium, water. Okay, so in reality, this is what the problem should have said. Okay, I'm going from water to air, and at that point, I find that my critical angle is about 48.6 degrees. So light that's coming from the water at an angle greater than 48.6 degrees doesn't actually make it out of the water. Okay, it runs at 48.6, it runs along the surface, and at 48.7, it doesn't come out at all. And that leads to total internal reflection, okay? Because when I exceed that critical angle, all of that light is going to be reflected back into the medium, okay? So none of that light is going to get out. I cannot see anything in that first medium, okay? And submarines use this effect to hide from sonar, okay? Because there are different temperature levels in water, and if they go below that, the sonar can't actually penetrate that barrier. Okay, so to detect submarines, ships have discovered ways to lower sonar past that cold barrier. Okay, here's another example. Okay, in this case, I have a thin sheet of glass, and light is basically just bouncing back and forth because it's completely being reflected as it goes through this piece of glass between the front and the back. Okay, and that brings me also to rainbows. Okay, because the index of refraction is dependent on the frequency or wavelength of the light traveling through it. So the result is different wavelengths get refracted slightly differently, and the angles of refraction will be slightly different. Okay, and that's how I get a separation of the colors, so that when I see a rainbow, okay, the colors of light have been separated out. Or if I go through a prism, okay, the colors of light have been separated out. Okay, so refraction concept 2. The faster medium has the greater angle. Okay, be careful to remember which medium or determine which medium is actually faster. Pitfalls that people have in terms of this is forgetting to measure the angles to the normal or the perpendicular. Sometimes the problem gives you the angle to the surface. Just be aware of that situation. Okay. The other pitfall that people run into is that situations where the critical angle plays a role. Okay. So always be on the lookout for things like the critical angle. Is any of the energy going to be transmitted, or is it going to be a critical angle situation? Okay. Thank you.